Now let's take an example problem to understand the ellipse and its various properties as we discussed in the previous sessions. So if I have a problem which says find the eccentricity foci, equations of directrices, length of major and minor axis. So I am trying to cover all the topics which we have discussed together to form the contents of the problem, so that we understand each of them through one unique problem. So we are going to find the eccentricity, foci S and S dash, equations of directrices, and length of lattice, major axis and minor axis, and of course length of lattice rectum of the ellipse, which is given by 3x square plus y square minus 6x minus 7y minus 5 equal to 0. So this is the equation of ellipse for which we are going to find each of these factors. So let's see how we can do that. Now as we see here, clearly the equation of ellipse is given in the non-standard form. So we are going to reduce this into the transformed form of the standard equation of ellipse. So let's see how we can do that. So the step 1 of proceeding with this to be reduced to standard form is that I take all x terms to the left and all y terms to the right. Therefore, if I take this equation with all x terms on the left and all y terms on the right, then I have this in this form, so that the next step involves taking all possible things which can be taken as common. Now here I see that 3 can be taken as common. So I take this as x squared minus 2x is minus of y squared minus 7y plus 5, because I want only minus to be taken common in this. So this I want to make a perfect square where a squared minus 2ab is there, but b squared term is missing out here to make this as a perfect square. So I add b squared and I subtract b squared, which I get here. So this continued with the next step gives me 3 times of this is a squared minus 2ab plus b squared, which reduces to the formula a minus b whole square. So this is a minus b whole square minus 1 square, which remains as 1. So with this formula out here, the similar type of expansion as done for this reduced to the formula, we get minus of y squared minus 2y, which on reducing to the formula comes as y squared minus 2 times of 1 times of y, which is a squared minus 2ab, and then plus b squared and minus b squared is what we add and subtract. Therefore, here b is 1, so we have b squared and this, which is added and subtracted for this. Therefore, on expansion of bracket, I get this to be 3 times of x minus 1 whole square minus 3 times of 1, which is minus 3, is equal to minus of this being a square minus 2ab plus b square is a minus b whole square, which is this whole square minus 1 plus 5, because 1 square reduces as 1 plus 5 is what we get. Now this on further expansion gives 3 times of x minus 1 whole square minus 3 is minus times of y minus 1 whole square minus of minus 1 is plus 1 plus 5. This on further simplification gives 3 times of x minus 1 whole square minus, if I bring here, I get plus y minus 1 whole square, that is equal to 5 plus 1, which is 6, plus 3, which is 9. So all constants brought together and added gives me 9. That implies I divide the whole equation with 9 so that I want 1 on the right side. So I get this to be 9 plus y minus 1 whole square by 9 is equal to 9 by 9. So with this division of 9 on both sides of the equation reduces to 1, because the standard equation always has 1 on the right side. Thus, this on simplification gives the standard equation of ellipse in transformed form. Therefore, the simplified form I would get as x minus 1 whole square by 3 plus y minus 1 whole square by 9 equal to 1. So this is still not in the standard form, because if I just have this further simplified as x minus 1 whole square by 3, which is root 3 whole square, plus y minus 1 whole square by 9, which is 3 square, is 1, is called the standard equation of ellipse in transformed form. Because the equation which is given in the form 3x square plus y square minus 6x minus 2y minus 5 equal to 0 has the equation which is simplified to the form x minus 1 whole square by root 3 square plus y minus 1 whole square by 3 square equal to 1, which is the standard form representation. Now here I clearly see that if I compare this equation with x minus h whole square by a square plus y minus k whole square by b square equal to 1, then I have my h which is equal to 1 and my k which is equal to 1 equally, and my a square which is root 3. Therefore a is root 3 and b is 3. Now clearly I see that a is root 3, which is approximately 1.7, and b is 3. Therefore b is greater than a. So here the condition is b greater than a, and therefore with this condition we're going to use the concept of identifying the eccentricity, foci, equations of Directrix, length of major and minor axis of the ellipse for this equation with h equals 1, k equals 1, a this, b this, with b greater than a. Now here we have h is 1, k is 1, a is root 3 and b is 3 with b greater than a or a less than b. Therefore, in order to find eccentricity E, we use the formula a square equal to b square times 1 minus a square. That on further simplification gives a square, which is root 3 whole square, and b square, which is 3 square of 1 minus e square, through which I find e. So root 3 whole square, which is 3, and 3 square, which is 9, times this implies this gets cancelled 3 times, 3 ones and 3 threes, and then I get this to be 1 equals 3 times 1 minus e square. which on further simplification gives 1 equals 3 minus 3a squared. That is, this will be 3a squared equal to 3 minus 1. That implies 3a squared equal to 2. That implies a squared is 2 over 3. A is plus or minus root 2 by 3. Now, since e lies between 0 and 1, implies e cannot be negative. So I take plus root of 2 by 3. So the value of eccentricity is root 2 over 3. Since e lies between 0 and 1, it cannot be negative. So I take the positive value e equals root 2 over 3. So the eccentricity of the given ellipse is root of 2 over 3 as here. Now next is to find the foci S and S dash. So we know that for a less than b or b greater than a, the foci are S, which is given by 0 BE, and S dash, which is given by 0 minus BE. For the standard form, my transformed equation as S equals H, comma, BE plus K, and this is H, comma, minus BE plus K, is how we get the two types of transformed equations. So this is nothing but given by H, which is 1, and B, which is 3, times of E, which is root 2 by 3, plus K, which is 1. So the focus is given by this, as we see. So this can be further simplified to be with root 6 plus 1, because this gets cancelled with this as root 3. Root 3 times of 2 is root 6, with root 3 and root 3 getting cancelled. And similarly, this will be H, which is 1, and minus BE, which is 3 times of root 2 over 3 plus K, which gives us 1 minus root 6 plus 1. So the foci are 1 and 1 plus root 6, and 1 and 1 minus root 6. Therefore, foci is 1 and 1 plus root 6, and 1 and 1 minus root 6 is how we identify the foci of the given ellipse. Now next is equation of Directrix. Equations of directrices. As we see, there are two equations of directrices. So for this, we know that the ellipse is going to look like this, where the directrices are here. So this equation of directrices would be 0b by e. So any line parallel to x-axis is y equal to b by e, and y equal to minus b by e. So we have the equations of directrices as plus or minus b over e. That is, my capital Y, which is y minus 1, because if I take capital X as x minus 1, my capital Y is minus y minus 1, is how we take the transformed equation. That implies y minus 1 is plus or minus b over this, which on further simplification gives y equals plus or minus 3 root 3 by root 2 plus 1. So there are two equations of directrices. So one given by y equals 1 plus 3 root 3 by root 2, and the other given by 1 minus 3 root 3 over root 2. So equations of lattices are this and this. Length of lattice rectum. Now we have the length of lattice rectum. There are two lateral recta, LL dash and MM dash, which are equal. We know that the length of lattice rectum is given by the formula 2a square by b for a greater than b, or b, or a less than b, or b greater than a. So for this case, the lattice rectum is 2a square by b, which on substitution gives 2 times of a square, which is root 3 whole square, by b, which is 3. So this on further simplification gives 2 times of 3 over 3, that is 2. Therefore, length of lattice rectum is 2 units. That's how we identify the length of lattice rectum for the given ellipse. So in this manner, we can continue doing the different parts of the question, like finding the extremities of the lattice rectum, which we compare with the standard form for b greater than a and compare it with the transformed equation, and we get the respective equations as obtained and the endpoints. So even the length of major axis and minor axis can also be simplified using the respective formulae as we discussed. Is how we understand the various properties which we can do as problems for the given ellipses. So in the previous case, we have discussed about position of a point. There were 3 cases that a point existed in the plane where an ellipse exists. The 3 cases where P lies inside, on, or outside the ellipse. Similarly, we're going to discuss about position of a straight line with respect to the ellipse. So let's see the 3 cases which exist in case of the straight line and the ellipse with respect to the position of a line with respect to the ellipse. So the position of a straight line has 3 cases, where the first case is if I have an ellipse, the straight line is like this, and the second case is when the straight line is like this, and the third case is when the straight line is like this. So these are the 3 cases which we have for the straight lines. One is the line is non-intersecting or disjoint or does not cut. Line is outside the ellipse, then it does not cut the ellipse. Here, line, part of line is inside the ellipse. That means the line intersects the ellipse at the most at 2 points. Now here, the line is touching the ellipse. So here are the 3 cases where the line is outside the ellipse, part of line is inside the ellipse, and here the line touches the ellipse. So with these 3 cases, we have that if the line is outside the ellipse, there is no point of intersection of line and ellipse. If the part of line is inside the ellipse, there are 2 points of intersections in the ellipse. If line touches the ellipse, there is 1 point of contact, which is this. So P is point of contact of the line with the ellipse. Here A and B are the points of intersection of the line and the ellipse, and here there is no point of intersection, is how we understand. There exists no point of intersection and no point of contact is how we understand the three cases of the line outside the ellipse, part of line inside the ellipse, and the line touching the ellipse. Tangent and its equation. So we have discussed about the tangent with the three cases of position of a line with respect to ellipse. Now let's see what is the equation of tangent of an ellipse. So for example, I take the ellipse in standard form with origin, and here is the tangent at P, or I have the tangent at P, which is x1, y1. Now how do we find the equation of this tangent which touches the ellipse at P, x1, y1, where equation of ellipse is s equals x squared by a squared plus y squared by b squared minus 1 equal to 0. So for this, of course, assuming that a is greater than b, I want to find equation of tangent of this with respect to ellipse s equal to 0 is given by the formula equation of tangent t at P x1 y1 with respect to s equal to 0 is given by s1 equal to 0. So this is the way we find equation of tangent. S1 equal to 0. We know what is x1, s1, and hence equation of tangent at the point P x1 y1 with respect to the ellipse s equal to 0 is given by s1 equal to 0. Now let's see the condition for tangency. When does a line act to be a tangent to the ellipse is what we're going to discuss here. By the topic condition for tangency. If suppose I have an ellipse s equal to 0 in standard form with x-axis, y-axis, and this, and for this ellipse I have a tangent, say y equals suppose I have this tangent to be y equal to mx plus c. Then for the ellipse given by the equation x squared by a squared plus y squared by b squared equal to 1. Of course here a is greater than b. So condition for this line to be a tangent to the ellipse x squared by a squared plus y squared by b squared equal to 1 is simply that c square equals a square m square plus b square is how we identify the condition. Or this can also be taken as c equals plus or minus root of a squared minus a square m squared plus b squared. So condition for y equal to mx plus c to be a tangent to the ellipse x squared by a squared plus y squared by b squared equal to 1 is c squared must be equal to a square m squared plus b squared, or c must be equal to plus or minus times root of a squared m squared plus b squared. Condition for tangency. Now as we have discussed with condition for tangency, let's recap with the condition for tangency connected with equation of tangent to the ellipse. Say for example, we have the condition for tangency as c squared equals a squared m squared plus b squared for the line y is equal to mx plus c to be a tangent to the ellipse x squared by a squared plus y squared by b squared equal to 1. So this gives us the condition that this has two values, that is c equals plus or minus root of a square m square plus b square. Therefore, I have two values of c which I can substitute for y equal to mx plus c. That implies these two values of c give me two lines, one given by y equals mx plus c, which is plus of root of a square m square plus b square, and the other given by minus, that is y is equal to mx minus of root of a square m square plus b square, is how we understand the two cases of y equal to mx plus the root and mx minus root. So these are said to be the two tangents for the ellipse. There are always two pairs of tangents for the ellipse in this case. Let's see how those two tangents look like, this and this, in the diagram of ellipse. Therefore, if I take the equation of ellipse in standard form, then I have the ellipse with major axis and minor axis, and hence this is the ellipse in standard form. And for here, if I have a point where the line is the tangent, I'd say this is given by y equals mx plus root a square m square plus b square. Then the other line with the same slope is a line which is parallel to this. Therefore, any line which is parallel to this line t1 and touching the ellipse s equal to 0 would definitely exist. There are two pairs of tangents which are parallel in the ellipse, as we have seen in the circle. Therefore, this tangent equally has a parallel tangent out here, so that this can be. Therefore, there exists tangent T2 which is parallel to this and also which is a tangent to the ellipse here. So therefore, this is the point of contact of this with this, and this is the point of contact of this line with the ellipse. And because this equation is given by plus root of, the minus root of is obviously a line which is parallel to the tangent drawn here and exactly which is having the same slope, and therefore these two lines being parallel, this equation is y equals mx minus root a square m square plus b square. Therefore, this gives us the learning outcome that there are always one pair of parallel tangents to the ellipse. So the learning outcome is there exists one pair of parallel tangents to the ellipse. Is how I come with the learning outcome for the ellipse. This tangent and this tangent are parallel. Therefore, T1 is parallel to T2. One of the tangent T1 given by equation y equals mx plus root a square m square plus b square, and the other tangent T2 given by y equals mx minus root a square m square plus b square. The pair of parallel tangents connected with condition for tangency. Now let's see the equation of chord joining 2 points. So for example, I have the equation of ellipse in standard form with x-axis and y-axis out here. Now for this ellipse in standard form, assumed as s equal to 0, with s being x squared by a square plus y squared by b square minus 1 equal to 0, then we know that a chord is a line segment joining 2 points of the ellipse. Therefore, let me take the chord which joins these 2 points P and Q, with P equals x1 y1 and Q equals x2 y2. So equation of chord joining P and Q given with P the coordinates x1, y1 and q with coordinates x2, y2. PQ is the chord, and we have equation of chord PQ is given by S1 plus S2 equals S12 is how we get the equation of chord. So equation of chord PQ joining the points x1, y1 and x2, y2 is given by S1 plus S2 equals S1, S2. The notations which we have already seen is substituted to get the equation of chord. Normal to the ellipse. What is a normal? As we have seen in the circle that a normal is a line which is perpendicular to the tangent and passes through point of contact. Here also we define normal in the similar manner. Say for example, I have an ellipse. And I have a tangent at P out here at the point P. Then the normal is said to be a line which is perpendicular to the tangent and passing through P. Therefore, this would be the line which is passing through P and which is perpendicular to T. So here we call this as normal and we call this as tangent. And remember, the normal is always perpendicular to tangent, and the special case being that it passes through P. And also to note, N passes through P, which is the point of contact. Is how we understand the normal to the ellipse s equal to 0. Equation of normal. Let's see, now that we have discussed about normal, next comes on what would be the equation of normal, just like the equation of tangent to the ellipse. So the topic is about identifying the equation of normal. So let me take the ellipse in standard form and define the equation of normal at point P, or the point of contact. Say I have the ellipse in standard form with center origin, and this is s equal to 0, where the equation of ellipse is x squared by a squared plus y squared by b squared minus 1 equal to 0. And say I have the normal existing at this point for this, where this is the tangent and I have the normal here. So I want to find the equation of this normal n, which is perpendicular to this at the point of contact P x1 y1. So equation of normal at P x1 y1 with respect to s equal to 0 is given by equation of normal n at P x1 y1 with respect to the ellipse s equal to 0 is given by a square x by x1 minus b square y by y1 equals a square minus b square. Assuming that x1 and y1 are not equal to 0 is how we define the equation of normal to the ellipse at P x1 y1. So therefore equation of normal at P x1 y1 with respect to the ellipse s equal to 0 is given by a square x by x1 minus b square y by y1 equals a square minus b square. Is how we understand the equation of normal to the ellipse. Now here it is very important to note that there are two special cases for equation of normal. Say for example, I have the ellipse in standard form as s equal to 0, but here there are four extremities, one being a dash and the other being b and b dash. Now as we know that if suppose I want to find equation of normal at b, then this is 0 comma b and 0 comma minus b. Therefore equation of normal at b, if I just would like to draw, I have a tangent which goes like this, and this is exactly perpendicular. Therefore the special case is the equation of normal at b and b dash are parallel, and these two being parallel, I have this acting as the normal. So the normal at b and b dash acts as the normal, which is y-axis. Therefore the special case is equation of normal at b and b dash is y-axis, or given by x equal to 0. Is how we identify the special case. Equation of normal at b and b dash is nothing but y-axis. As can be clearly seen, a tangent drawn is perpendicular to the line passing through b, which is nothing but y-axis. And similar is the case with b dash, where a line passing through b dash and which is perpendicular to tangent is a normal. Therefore giving us the outcome that equation of normal at b and b dash is y-axis, or x equal to 0. That is, whenever I have the x coordinate as 0, I get my normal as y-axis. That is, the x coordinate, which is x1 equal to 0, implies normal is y-axis. Is how I conclude the formula. X1 equal to 0 implies normal equal to y-axis. Similarly, the next concept is about identifying that y1 equal to 0 implies normal is x-axis. So let's see how y1 equal to 0 leads to normal as x-axis. Next, we see the equation of ellipse. First, let's draw the standard ellipse out here. X-axis, y-axis, and the ellipse. Now for this ellipse, we know that the extremities are a dash, b and b dash, and we know that the coordinates of a are a0 and the coordinates of a dash are minus a and 0. So let's draw a tangent at a, that is a comma 0, and clearly we know that the tangent out here, say this is t1, is perpendicular to x-axis. Clearly this will be a perpendicular to x-axis. And similarly, a tangent drawn out here is perpendicular to x-axis here, which makes us understand that the line which is perpendicular to the tangents t1 and t2 and passing through a and a dash is nothing but x-axis, giving us the same conclusion as in case of b and b dash, which says that for this circle s equal to 0, equation of normal at a and a dash is given by x-axis or y equals 0 is how I conclude the x-axis. So in this case of equation of normal is x-axis or y equal to 0. In the previous case it was x equal to 0. Therefore, in general conclusion, for any other ellipse which is not standard, if I have my y coordinate as 0, I get my normal as x-axis. Therefore, y1 equal to 0 implies the normal is x-axis or y equal to 0 is how I conclude the normal in general case. x1 equal to 0 implies the normal is y-axis. y1 equal to 0 implies the normal is x-axis is how we understand the concept of special cases connected with equation of normal. Now let's see the equation of tangent in parametric form. Now that we have discussed about parametric equations of ellipse or the parametric point on the ellipse, let's connect the equation of tangent with the parametric point. Now we know that if suppose I have equation of tangent which I need to find in parametric form, so let's see how we can find equation of tangent in parametric form. So let's take the tangent and its ellipse in standard form. So I have my ellipse out here, and let me have the tangent out here. So this is the tangent T which touches the ellipse. So let me say the tangent touches the ellipse at P of theta. Now this being the parametric point, we know that the parametric point P of theta is given by A cos theta and B sin theta, assuming theta lies between 0 and 2 pi. And let me say equation of ellipse is S equal to 0. Then assuming on S, we know the standard form of S is x squared by a squared plus y squared by b squared minus 1 equal to 0. Of course here a greater than b. So therefore equation of tangent at the parametric point with respect to the ellipse S equal to 0 is simply given by x cos theta by A plus y sin theta by B equals 1 is how I conclude the equation of tangent. Therefore, equation of tangent T at the parametric point P of theta is given by x cos theta by A plus y sin theta by B equal to 1, with theta ranging from 0 to 2 pi is how we understand the equation of tangent in parametric form. Now similarly, let's see the equation of normal in parametric form. So as that we have discussed about equation of tangent in parametric form, similarly let's identify the equation of normal in parametric form using the parametric point P of theta. So here is the ellipse in standard form. And I have, say, the tangent T at this parametric point P of theta. So here is the parametric point, which is the point of contact of tangent with this, then clearly the normal is a line which is perpendicular to this at this point P of theta. Now we have to find the equation of this normal using the parametric point P of theta, which is possible by taking the equation of ellipse as s equal to 0, that is s is x squared by a squared plus y squared by b squared minus 1 equal to 0, and of course a is greater than b. So let's see how we can get the equation of normal. Equation of normal at the parametric point P of theta with respect to the ellipse s equal to 0 is simply given by the equation of this normal is ax by cos theta minus by by sin theta equals a square minus b square, but with the condition that theta is not equal 0, pi by 2, pi and 3 pi by 2. The reason is if theta is 0, I get this at this point theta is 0, and at this point we say theta is pi by 2, and at this point theta is pi, and at this point theta is 270, that is 3 pi by 2, and here it is 0 or 2 pi. Therefore clearly we see that if the parametric point is theta is 0, then the x-axis will be the normal. That is, for theta equal to 0 or pi implies the normal is x-axis, or y equal to 0 is how we identify this. And therefore when theta is pi by 2 or 3 pi by 2, the normal is y-axis. That is, theta is pi by 2 or 3 pi by 2 implies the normal is y-axis, as can be clearly seen here, and that is x equals 0. That's how we understand the difference between the special cases and the general equation of normal, which is given by ax by cos theta minus by by sin theta equals a square minus b square at this parametric point P of theta, with these two being the special cases. It is mathematically proved that there are 4 normals which can be drawn from a point to the ellipse s equal to 0. So for example, I have an ellipse out here, and if I have a point P, x1, y1, then at the most there are 4 normals, because there are tangent which pass through one point is how we identify. This is normal 1, so we identify that there are totally 4 normals which can be drawn. If suppose I assume this to be tangent 1 and I assume this to be tangent 2, then this is normal 2, and if I assume this to be tangent 3, then I have this to be normal 3, and this is tangent 4, then this is normal 4. Is how we understand totally 4 normals which can be drawn through the point at the most. So 1, n1, n2, n3 and n4. So from a point P, x1, y1, I can at the most draw 1, 2, 3 and 4. So these are the 4 normals which I can draw from a point P, x1, y1 at the most. So therefore, the property says that 4 normals can be drawn at most from P, x1, y1 to the ellipse as equal to 0. Is how we identify the properties of normals from a point P, x1, y1. So at most there can be 4 normals. It can be either 1, 2, 3 or 4, but not necessarily that it should be 4. It should be either 1 or 2 or 3 or 4 normals which I can draw for the ellipse. Is how we understand the properties connecting the number of normals from a point P, x1, y1. Director circle. Now let's see how a director circle is obtained from an ellipse. Now see here, if suppose I have an ellipse and I take the pair of tangents which are perpendicular to each other. Say my pair of tangents from here and here are perpendicular, with this one pair being out here. And similarly, let me take another point from where the 2 tangents are perpendicular to each other. So the pair of tangents which are perpendicular, the locus forms a circle around the ellipse. It forms a circle around the ellipse, and this locus of all pairs of tangents which are perpendicular with respect to the ellipse is said to be a director circle. So director circle is the locus of all the points of intersection of the perpendicular tangents, one of them being P, Q, R, etc. So all the pairs of tangents which are perpendicular, the points of intersections are joined, then it forms a circle called the director circle. And director circle is said to be with equation connected with the circle. And very important point is center of ellipse and center of director circle are same, that is they are concentric. So center of director circle is equal to center of ellipse, is how we identify. And next I identify that radius of director circle is root a square plus b square, where this is the standard ellipse, x square by a square plus y square by b square equal to 0. So is how we understand the properties of director circle. Now let's see how we can find the equation of director circle. Therefore, if I have my x-axis and y-axis, and if I have my ellipse out here, we know that the center of this ellipse is 0, 0, and this equation is given by x square plus y square equals to 0. That is S given by x square by a square plus y square by b square minus 1 equal to 0, with a greater than b. Now for this, we have the director circle which gets connected with the circle with the ellipse. So I have my director circle which is concentric with the center of ellipse. Therefore, center is origin and radius is root a squared plus b squared, implies equation of director circle is given by x squared plus y squared equals a squared plus b squared is the equation of director circle is given by x squared plus y squared equals a squared plus b squared. And if I take any point on the director circle, that means I can draw two tangents to the ellipse, and then I can draw two tangents to the ellipse T1 and T2, which are always perpendicular to each other, is how we understand the director circle connected with the ellipse. When I draw two tangents from a point on the director circle, those two tangents act as perpendicular tangents to the ellipse, is how we see the connection of director circle with the ellipse. Equation x squared plus y squared equals a squared plus b squared.